All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk. But if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Dr. Brandstetter, who did his PhD studying Higgs boson decays at the CMS experiment at the Large Hadron Collider at CERN. In 2018, he joined the Sepp Hochreiter's group in Linz, Australia. In 2021, he became the ELLIS postdoc at Max Welling's lab at the University of Amsterdam before joining the newly founded Microsoft lab in Amsterdam. During his time at Microsoft Research, Johannes was working on scaling up of AI-driven physics surrogates, most notably for weather and climate simulations. In October 2023, Johannes moved back to Austria and started a new group, AI for Data-Driven Simulations, at the Institute of Machine Learning at the Johannes Kepler University in Linz. Additionally, in 2024, Johannes was chief researcher at NXAI GmbH. Recently, the Johannes co-founded Emmi AI, where he is currently the chief scientist. Today, Johannes will talk about the next wave of scientific breakthroughs is in the latent space. I'm sure we are going to hear a wonderful talk. Now let me ask a somewhat informal question to him, just to get to know him a bit better and make this seminar a bit informal. So here is my questions for you. I know that you love mountains and you are in Austria right now and near the Alps mountain. What is the maximum height you got into?
That's a good question. I have to say there's a lame answer to that. I only was at the highest peak of Austria, which is 3,800, which is not quite impressive compared to other peaks in other parts of the area, but it's at least the highest in our country.
Oh yeah, so okay, so you conquered the highest in Austria.
There's nothing higher to conquer, no.
Okay, so the next step would be the higher points in other countries.
Yes, exactly.
Okay.
You would need to go to Switzerland or Italy.
I see. All right, the floor is yours.
Yeah, thank you very much for the introduction. Thank you very much for having me. I'm quite excited to be here. I talk about latent space. I talk about science being done in a latent space. I will have this a bit intertwined with my personal view on spatial temporal challenges which we face in modeling. This very much comes from the fact that we all hear so much about LLMs and about scaling up and about solving larger and larger problems, maybe neglecting a bit the fact that tokenization, or how we present problems even to an AI system, is something which is very different in physics and in engineering and in science in general compared to language. And even if we think of language, just if we think of how long it took the whole AI field to come up with the right tokenizers, it might be not so straightforward to come up with the right way we present science to large scale models. And even if we know how to present science, how we even model like spatial temporal relationships. I started to really think more about many different engineering problems in the last 2 years, coming from I have to quote Tanya, sorry for that if you listen in. This is a quote I extremely like, and I heard 2 months ago. And this is, I think, what people in machine learning should try especially in science, to attach yourself to solving a problem, to coming up with the best methods or the best ways to solving a problem, and not attaching yourself to a method, basically being, I've invented X, Y, Z, so this is the best method, but rather using or rather really trying to solve problems. That is what I want to talk about in combination with my personal view on latent space. I have to say, I don't want to make any advertisement about my company because this is a science talk, but I have to ground a bit or motivate a bit the work I'm talking about, the problems I'm talking about with the problems of engineering which we're tackling in the company. So I will give you a very quick elevator pitch, which I would give to an investor. So if you're an investor, I have to tell you that the field of engineering, as we currently know, compared to language vision, is very, very unexplored. But if you think of the true potential, which is in all these engineering problems, there's many, many verticals you can untap. If you think of manufacturing, logistics, engineering, and my personal bet is that the biggest market to unlock with AI is data-driven simulation and digital twins. So this is what you would say to an investor. But if you were to speak to a colleague who is doing AI as well, and if you want to convince him to join your company, you would say the following. You would say something like that. It's basically quite well understood how we model text and how we model images, but how would you model, let's say, a Formula One car? How would you solve, or how would you model the flow field around the Formula One car? Given that if we do a proper CFD simulation, which is done in a three-dimensional space around the Formula One car, you would then need 1 billion mesh cells. What's the best way of constructing surrogates, neural network, help to model that? Similarly, I asked myself like 2 years ago, what's the best way to model multiphysics phenomena? Multiphysics phenomena as an example here, just ignore the lower line. You have these particles, 500,000 of particles, they are bouncing around, driven by air which is coming from below, and which basically is doing an interaction. But in order to model this interaction, it's very, very complicated dynamics, which is very hard to understand. So what's the best way to model that? And this is, in my opinion, still a very, very open question, because the field we are operating in is in the whole is basically in the range of where fluid dynamic is happening, where CFD is happening, where mechanical simulations are happening, and where very similar relevant simulations are thermodynamic simulations, and so on and so forth. So this is the field we're playing. This is the field we're trying to come up with new breakthroughs. And this comes up with my personal view of challenges, or of how we model space and time, because all these simulations have something like a spatial and temporal component. And when we talk about space and time, we have to remind ourselves of how we actually model space and time in numerics. And numerics, I want to stress at the beginning, is a field which works since 200 years. This is a field which is super well developed, where we know how we get guarantees, where we know what type of algorithm works for what type of problem, and how we're designing this type of problems. There is one very rudimentary rule of how numerics works for temporal problem, and this is very, very a rude approximation, but I think it's still valid for 99% of the problems. So what you would do is you look at your problems, you look at your equation, and you look at the problem as two type of sub-problems. The one is the right-hand side, and these are all the physics operators like convection, diffusion, advection, whatever, which you can write as spatial derivatives and combination of different fields you have in your system. And that's actually the tricky part, to estimate all these derivatives, all these operators by some tricks like finite difference, finite volume, and different schemes. And then the second challenge, or the second sub-challenge, is to use this estimate, which you do on the right, to do an update on the whole system on the left, which is usually then an ordinary differential equation, which just means a temporal update, because you have eliminated all these other spatial terms by using some approximation to them. easily you can see that if you look at the finite difference scheme, which has different ways of approximating derivatives for by using neighboring pixels and combining them in a way that you get an approximation with some error guarantees depending on how close you use and how many neighboring points you take. So this is a way how machine learning started and I look at the progress of machine learning in model spatial temporal system by exactly at looking this equation. So the first works which came out and which were really eye-opening for me were to come up with estimates for the right-hand side. So for example, the Google paper from 2019, as I put here on the right, they come up with estimates for these spatial derivatives, combine these estimates given by the neural network and make an update in time. Similarly, the group of Peter Battaglia at Google DeepMind started to use estimates for the acceleration of each particle in many different simulations to give an update or to feed this acceleration to a numerical solver, which does an Euler update and updates the next position of each particle. So what these systems are doing, they solve or they give a good approximation for the right-hand side, even an approximation which might be better or more accurate, but at least faster than the predictions you would get from numerics. I was very intrigued by that and we started to work on that roughly, I think, 6 years ago, using this type of models. The problem is, if this is a failure case, you would normally not show failure cases in a presentation, but this is a very typical failure case. You see the ground truth on the right and the prediction on the left. And it's the similar network. You predict acceleration of these particles, you propagate them forward in time. Problem is that this is a very complex geometry. It does not look complex, but the surface is a triangularized surface and these particles interact with the surface. So somehow I have to model the surface interaction also with a node in this graph network. And it's just very hard to get these interactions right. And if you make a tiny error in these interactions, if one of these accelerations is predicted wrongly, and then you do the temporal update, you make the next prediction and so on and so forth, errors accumulating, which leads to catastrophic behavior quite quickly. So obviously it took us some time to get it to work. At the end, it worked and the network was modeling this quite accurately. But the problem was really, it was extremely hard to get it to work. It was really challenging. And we somehow always had the feeling we're squeezing the model into this numerical framework that it works. I would say big shout out to Andreas Meyer, who did that back in the days. It was a bit unsatisfying to not the project itself, but to see that the limitations of machine learning in this type of errors compared to how machine learning was excelling in other areas. And that got me think, and I didn't have an answer back in the days. What then happened in the community is that people started to jump over this differentiation between spatial updates and temporal updates. What people did next is they predicted the next state of the system basically in one go. So they put in the state of the system at time point t. They predict how the system is evolving in t. There is many works. I think one of the most impressive areas is weather modeling, which started, I don't know, roughly 3-4 years ago, and which leads to this impressive weather modeling like GraphCast, Aurora, and so on and so forth, which are now on the market. This is a triumph on modeling very difficult systems on very high resolution by using the network as simulator for the system, predicting the state of the system forward in time. Again, we have basically got rid of this temporal problem. What is a bit, what we exchanged the complexity of the geometry to higher resolutions, more complex simulations, and we exchanged graph networks to something like transformers in the end. And now I want to go back to typical engineering use cases, which you have when you look at problems as I showed in the introduction. You have a very different problem setup. So you have this ratio of cells to information, which is very different than in videos and also in weather, where the information is very fine-grained. In weather, the information is not that fine-grained in many of these information in these scenarios. So the ratio is just different. It's very geometry driven. So geometry is a central part of these problems. Not only that there you have flows around geometry and mixing stuff, but you also the geometry itself can form. So if you have like injection molding, or if you look at some material which is bending, geometry itself is forming depending on stresses it is exposed to. Next, you have a lot of interactions of particles, fluids, geometries. And what that means that you really have to rethink the way of how encoding works. Before we go to the encoding, I would say the name of the game is to use the concept of neural operators, to use the concept of thinking of functions, of thinking of underlying functions from which you sample, and to think of the input as a function from which you sample. It should not matter how you sample from the input. It should not matter how many points you sample. You should come up with the similar representation, if not the same representation of the input. That is enormously important, because then you can use this representation in more compressed latent spaces, we will see later. The way we are thinking about it, and there's I think many different works in that area which are doing similar steps, is by coming up with an efficient latent space modeling, which consists of a compression and a decompression algorithm, and this decompression is very general. It means that it takes into account the different points, and it has a property which means discretization convergence, meaning that if you have a different number of points, you would come up with the same representation, and if you query the model at different output points, you basically come up with sampling from the same function. Intuitively, just explaining the concepts, obviously the devil is in detail, and each of the steps is tricky, and it needs to be seen what's the best way of doing it. I think I walk you through the steps now. Think just of a bunch of particles you want to encode. One thing which many of the simulations have in common, as I said, the ratio of information content is very different than videos and images. That means to some rate you can do a heavily subsampling, which not only leads to data augmentation, but which also reduces the problems drastically. We're talking about 99% of subsampling in some cases. So you can do this heavy subsampling, which is in one way or the other very different to the systems we know, and then basically you need to have two steps. The first is a local aggregation. That is very important, because even if your subsample systems might be extremely large, so the aggregating of the information needs to be local, that you can distribute the problem over GPUs, and then you can reduce each GPU, or each GPU is only locally looking at neighboring information. And when you have this so-called, as we call it, supernodes, these so-called local champions, which have aggregated information, you basically are already in the setup that you have something like a token. Then you add information on top of it, and then you get your latent space, which you can rather either compress further, or you add some additional information on it. You can mix this latent space with other encodings and whatever you're getting. So the gist here is that we have in engineering, and many engineering use cases, also in many physics use cases, they are very much intertwined. You have a subsampling strategy which needs to be very well understood. That is obviously the big challenge. I'm not saying that this is solved. You have a local aggregation step, and then you have a global aggregation step. Then you get a very compressed representation. And now if I show you that the similar input, but with double as many points, you should get the same representation, or a representation which is very close to this representation. The decoding happens in a similar way, just the other way around. I'm not focusing too much on that, because that puts away too much of our time. More important or more interesting than this spatial aggregation is the concept of time. We are currently in a discussion about what's really the best way for LLMs. Is it really predicting the next token, or is it more intuitive to predict like a whole text and iteratively refine it? Similarly, in physics, predicting the next state of the system comes with lots of limitations, like systems are not consistent, system starts to hallucinate, and so on and so forth. What is, however, really important to note is this machine learning is very good at understanding structure. It's very good at understanding general structure over different time steps. But what machine learning is not good is extracting very, very precise update rules. I want to now make a bit of a switch and talk about one specific project, which is only to motivate my thinking of time, because doing this project somehow really changed the way I think of time, and I think of how we should model time. It is a project which it's not publicly available yet. You will see very soon. And what we're trying to do is compress some data from black hole mergers, so from these massive stars which merge, which are modeled by general relativity simulation. General relativity simulation means that you're modeling a four-dimensional space-time given by Einstein's field equation, which look very neat. But if you write it down, these are 10 coupled tensor equations, which are very, very nasty and which are very, very hard to compute. And if you were to run these numerics, or if you look at the numerics from this one black hole merger simulation, you come up with data which is around a terabyte of data, which is super hard to store, which is super hard to handle. And even if you want to extract physics from this data, like geodesics, it's very hard, because you need the underlying mesh, which is changing adaptively. If you go to things like singularity, where you need much finer mesh points in order to get the derivatives roughly right. So this is a very challenging way in just not only storing the data, but also how to obtain physics. We had the idea to use neural fields as scene representation, which allow us to compress this simulation very heavily, and then with automatic differentiation allows us to reconstruct physics. I'm not spoiling this more. I just wanted to show you that I'm really excited about this project. You can look it up yourself as soon as it's out, and you can judge yourself. The important point is I wanted to show you my excitement, because if you're excited about something, you think about it a lot. And I'm thinking about it a lot, which also made me rethink the way we look at time. Because at some point in the last couple of months, years, half a year, I started to not think about space and time as two different things. I started to think about one thing. And that is very interesting. I'm actually at the moment in New York. I flew in here, I think on Monday this week. Usually when I fly somewhere and you ask me where are you going to fly, I have this mental picture of going from Europe to the US, and I have this arrow which basically follows the geodesics. This is the mental picture I have in my head. So when I explain what I'm doing, when I explain where I'm flying, I literally see this little arrow representing the airplane going from Europe to the US, and going like a movie, following a path. And I realized this week when I was asked at the airport where you're going, that there was no arrow moving. It was like this geodesics was there. So basically the line was there as if there is no temporal component of it. So I basically my head erased this temporal unfolding and made a straight line of it, or a geodesic out of it, which is kind of interesting, because this is coming from this way of thinking about relativity. And this is a very important concept in neural networks now as well. So let's first go to the latent space, do all these things which I explained before, but now use really the power of latent space. There is one fundamental or one game-changing work for me in the last 5 years. I mean, there's many game-changing works, but one which is really game-changing for me is stable diffusion. Not because we can get such nice pictures of dogs and whatnot, not because it basically is something which starts in Europe, but because of the concept to train two separate models, an encoder and a decoder, which give you a very compressed representation on which you can run your diffusion process. That you can really decouple the training the model from how we encode scenes. And if you think of physics or engineering, you can really decouple the way we model our system, or we emulate our system with the way how we represent our system. And that is very, very, very appealing. The next thing which made me realize is that obviously the stable diffusion gang was making progress, and at Stable Diffusion 3 is about modeling videos. And the work is called Align Your Latent. It's following the similar principles. I'm not going into detail, but what it has is it has this additional temporal axis. So it's modeling time, and it's basically aligning the latents over time. It's treating the whole thing, sorry for the misuse of the word, as a tensor, and it aligns over the temporal dimension. And that is really interesting for me, because suddenly we think of this latent space as a compact tensor over which you try to make things consistent, which is very much from the view I had from this general relativity space-time thinking. And this is an interesting concept, because we have this four-dimensional space-time, which we know from general relativity, and we see that that video generation actually allows us to model time as another dimension over which you align. So the question is more and more, is autoregressive modeling really the right choice, or should we think of something like a temporal alignment? Interestingly, I really start to rethink if we model that language even right, because always predicting next word and the next word and the next word is how a human would do it if you speak, because you basically you speak, or if you write, you write the next word, but in the end you have already a concept in your mind. So wouldn't it be better to predict the whole text at once and then iteratively refine the text? So basically allowing the output to look back and forth in the future and to align all these tokens. There is very nice works in that area, which are, I call it rolling diffusion models, mostly inspired by this paper of David Ruhe and colleagues, but there is similar concepts now happening in latent space and for LLMs. And what these rolling diffusion models are doing, they have a diffusion process at each time step independently. So basically each time step diffuses depending on how far it is away from the current time step. So the farther you're away, the higher in this diffusion window, in this time window, the farther you're away, the higher is your noise level. And the more you come to the actual time, the more the noise is decreased. Interestingly, you basically cross the tent, you align between these diffusion steps. That means you always you diffuse depending on what the future and your past is telling you. A very interesting concept, very not how we would do it numerically, but very much how it makes sense from a machine learning perspective. And I like this concept, and this is very much in this way of rethinking time. There is also this interpretation of diffusion models. There's this extremely nice blog of Sander Thielemann that there's different interpretations of diffusion models, and one interpretation is to see them as a autoregressive model in the frequency space. So iteratively you get better modeling of frequencies, you get better understanding of frequencies. The lower the amount of noises which you're reducing, the more you are in the higher up you are in the frequency spectrum, because there is this relation between low frequency which have high magnitude and high frequency which have low magnitude. So meaning having a noise with low magnitude, meaning you're refining high frequencies. We did a similar work on PDEs. So we reuse the diffusion concept to iteratively refine higher frequency components in PDEs, coming very much with from the similar vein, so that we shift so in general, shifting the autoregressive part now into the frequency domain and outputting more things together at once. So this brings me now to the final part. I tried to introduce the concept of spatial challenges, which result in a way that we need a better way of to compress, to encode simulation into latent space, or compress scenarios, physics, or whatever you want to call it, into latent space. Coming or aligning with the concept that meshes are extremely huge, and the degrees of freedom we are modeling there are small, often small in comparison to what we usually experience. So we come up with encoding and decoding challenge. Secondly, there is this temporal challenge, which somehow relates to generative modeling, iterative refinement. Now coming to a few use cases. Telling you at the beginning, we had this rotating drum where we had these particles, and these particles were not, or it was much more challenging than expected to model these particles, because we were putting everything into this neural network in this numerical way of predicting accelerations and then updating the positions. This is from a recent work we did, where we were actually modeling, I think this is 300,000 particles, and we're modeling these particles going down in this hopper, as it is called. You can think of this as grains. The mental shift we did is that we went away from particles. So we treat every particle as a realization of something like a displacement field, and we model the whole process as just a field changing over time. Actually, it's not 100% correct. We have two fields, like we have a occupancy field, which tells you if there is mass or not, and this displacement field, which tells you what's the displacement vector at each point in time. That reduces the problem drastically, and that's how a neural network thinks about it, because neural network is very good at learning a continuous representation, at learning how a continuous representation changes over time, and equating this continuous representation to the actual physics we're modeling. It's very interesting because what you see on the right, that's the output of the neural network. As you see, it's a field, it's not the particle. And obviously we cannot construct particles because the network representation is continuous. But this made these problems, or finally, this was closing this 5-year gap I had in my head of how that it's not very natural to model these particle systems with modeling each particle interaction, but instead trying to model the whole behavior at once. And similarly, we came to this more challenging problem of having this, as I introduced before, as having this multiphysics problem where you have these particles bouncing around and interacting with a fluid which is coming from below, which is super challenging. But now you can play the game. You can look at particles, encode these particles by first subsampling them, then encoding them locally, and then basically making global interactions. And similarly, you can encode the fluid components, which you see on the right, similar to how you would encode a 3D, would do a 3D tokenization with vision transformers. Then you have two representations in the latent space, and they just interact with each other because it's very natural that these two representations interact, because that's what the physics is doing as well. Particles interact with the fluid. And then we use these representations to decode, again, a field. In that case, as you see on the upper part of the simulation, the lower part of the simulation on the left, these are some isosurfaces of the displacement field, because we cannot output particles, which works very, very nice. So, and then in the latent space, obviously, if you want to have this temporal modeling, you can make all these tricks about, as I said, diffusion model and so on and so forth, to get consistency, to get things modeled correctly over time. So suddenly we managed to get a very complex physics problem into a representation which you can actually work on and have using all the tricks from computer vision, all the things which are shown by us from people working on stable diffusion and follow-ups, apply this to very complex physics setting and getting a way of handling this. There is another thing which I'm quite excited about, this concept of latent space modeling, and that is that you can decouple the way what you encode and what you decode. I think this is a super important concept in many areas, mostly in areas which are relying on a mesh. If you talk to a CFD expert, he will explain to you that getting the mesh, the correct mesh on which you can run your simulation is actually the painful part, because, or is at least as painful as running the CFD simulation, because the discretization, the convergence of the simulation, and so on, and guarantees, they come with the choice of the mesh. So if you want to make an engineer really happy, you avoid both the meshing and the cumbersome part of running the simulations. And meshing is not only a problem in CFD, it's in many other problems where you run a simulation which is based on a mesh. It's just that CFD is very easy to explain, because we have these nice data sets of cars which you can show. What that means, if you're able to encode different ways of represent the mesh, either by having a simulation mesh, or by just having a CAD geometry, or by having the output of a large language model which describes the geometries or whatnot, you can get this latent space representation. And then what you can also do, you can predict different things. You can predict on the surface, you can get unified prediction for drag and lift coefficients, for if you can look for cars, you can predict in the volume around the car, and so on and so forth. And even if you have interacting systems, you can use this unified representation. So this decoupling, or looking at this latent space, allows us to mix physics, allows us to decouple the way we encode and decode, and therefore opens up a very new door and very new field of modeling. And then there is this thing that you can do really crazy things with that. And I'm at the university only for 2 years now, I think, for 1.5. And I started to have really, really smart students. Unfortunately, not every student is doing all the time what you tell them to do. And there is this special type of stubborn students who do things even if you tell them that it's not a good idea to do that. One of these students is Florian Sestak. So he basically was very keen on doing molecular dynamics modeling. So molecular dynamics modeling is the way of what the challenge is. You have a molecule and you want to predict how the molecule moves over time. The problem is that if you model that numerically, you solve a stochastic PDE and SDE because of this Large Hadron dynamics, which introduces stochastic noise terms. And if you want to model that from a neural network perspective, that means that for each future step, you get a different probability distribution of where these atoms are. That is the name of the game, modeling the trajectory of molecules with a measure of probability distribution, how they are evolving over time. Classically, you would use something like a graph neural network or a transformer where each node represents each atom represents a token, because this has a very, very strong inductive bias. It is mass conserving. So each atom is represented, and a node in a graph network is not destroyed. So you're not destroying mass. The neural network has automatically the number of atoms right. That's how you should do it. But if you want to do it as a latent space modeling, you're destroying mass. This is not good. That's why I said, I think even if you're excited, Florian, you cannot do that, because the systems we showed you before, you have a bulk modeling, you have this material running out, you have this general behavior which you're trying to learn. It's the same behavior if you have 300,000 particles, or if you have 300,000 particles and 7 additional ones. That the overall behavior is not changing. The particles are not so important. Very different to molecules. On the other hand, Florian was very, very motivated by this latent diffusion concept, this latent modeling, and how we use the latent space for really learning dynamics. And the interesting idea, the way this was made to work, is by including some sense of ID tracking, using the benefits of a latent space, but actually adding some IDs to the atoms, that the encoding is guided by IDs, and we learn to restore these IDs. So even if we get into an unstructured space, this encoding is so powerful that there is meaning to this unstructured space. It's very, very counterintuitive, but it works extremely well. And this is one of the times where you actually realize that students are smarter than you, and you basically just let them do whatever they come up with, and be amazed by the results. So how this works conceptually, you add some IDs to it. So the input tokens have now a position feature, but also an ID, and you train an autoencoder to encode and decode this representation. And then in the latent space, you can use this modeling, this generative modeling. So what this is doing is on a molecular modeling, on a molecular level, a very similar concept that we see in latent diffusion, but just using the concept of having a very different encoder, which takes information of atom types, and using a latent space where you model the temporal evolvement, basically again as a tensor where you attend over the different time dimensions. So this is a bit how you can imagine. You get the encoding, and then you in the latent space you learn this diffusion process. Finally, one work I want to talk about, because this is science talk, which excites me a lot, and where you see the power of latent space modeling, is if you go to simulations which are even higher dimensional. And one example of those is nuclear fusion. In nuclear fusion, when you want to model the turbulence, you would go to a 5-dimensional framework, which is called karyokinetic framework, where you have 3 spatial dimensions and 3 velocity dimensions. One of these velocity dimensions is canceling due to symmetry reasons, so you end up with evolving ions and electrons in terms of distribution functions, and that allows you to model turbulence. Needless to say that this is very cumbersome numerically. A neural network can have a big improvement there. Again, it's the same game as we know all the time in what I showed. You have a lot of you have 5 dimensions to compress, so you need a very good compression, you need a very good encoder to come to a latent space representation. But I think now it gets even more clear that we need a latent space representation on which we can run our models, on which we can run our predictions, on which we can use our temporal updates to get forward in time, to understand and to analyze the systems and to make prediction. And the harder these challenges are, the harder the systems are, the more the benefit of latent space modeling, the more the benefit of having these strong temporal models is becoming. And this is basically coming slightly slowly to the end of my talk. I first of all, please don't take me too serious. This is my personal view of modeling, my personal struggles I had during my last years of understanding what's the best way of modeling space and time. I'm coming from the field of engineering, or I'm addicted to the field of solving engineering problems. Engineering problems, in my opinion, or many of these problems, will only be solved in the latent space. We are very lucky to have such a bunch of smart people from computer vision who show us what needs to be done. The temporal challenge, I think, has to be completely rethought in machine learning. I think temporal modeling is very much not solved by autoaggressive modeling. So we will have to switch to a more chunked-wise generative modeling approach. And again, time and autoregressive modeling have to be rethought. And that's the end of my talk. I think I'm in time, and obviously would be very happy to answer questions.
Thank you so much for the wonderful talk, as we expected. Yes, that was fascinating. Thank you so much. Yes, let's have a Q&A sessions. If you have any questions, please unmute yourself and then ask questions. Maybe I can start. In general, like big picture, this latent space, yes, I mean, I do agree that that's very important. But in order to form the latent space, you must have first some high dimensional data you have generated. And if, for example, if you are relying on the generating data on those high dimensional simulation, such as 5-dimensional gyrokinetic simulations, that takes a lot of times. So the generating data itself can be very challenging as well. So how would you, if you have any thoughts about that?
That would be actually now the topic for the next talk, right? So we talk. I mean, it's obviously it's the absolute first question to ask, and it's a great question. So I would say this talk was, I talked about modeling. So how we model things. Obviously now, if you really want to get an impact, you have to really understand to which problems you attach yourself. That's why I said it in the beginning. And these machine learning models are only powerful in combination with data. Certainly the answer is not to use all the compute and all the compute hours to get them a few numerical simulation which you can train on. That's like this chicken egg problem. I think that you for example, in many of these simulations, you can produce much cheaper simulations very easily, and basically train your models already on this easier simulation, on this more coarse-grained simulation or low fidelity simulation before actually going to the high resolution simulation. But technically, the nice thing is, if you have kind of a latent space approach, you can train these latent space models, and you kind of, the only thing which you really need to be sure is encoder and the decoder are correct. And therefore, you can also have a lot of, call it transfer learning, call it different data sets, calling different modalities. You have the chance to include a lot of more data types, a lot of more data into this modeling. So I can't give you a concrete answer of how you would circumvent this problem of generating data in the first place, but I can only say that if you have such latent space architectures, it's much easier to deal with different amounts of data, which in the end might enable us to understand better what kind of data you actually need to really get fast surrogates for a specific problem.
Yeah. All right. Well, thank you. So the questions are piling up. Khalid is asking. Khalid, actually, if you can unmute yourself and then ask it verbally, that would be awesome. Would you mind doing that?
Hi, am I audible?
Yes, you are audible. Yes.
I just have a very basic question. Is that like, I completely agree that when you use like sequential models to model the latent vectors like LSTM, RNNs, and transformers, the performance usually degrades over time as they are sequential. But this is a very basic question. How would you think of incorporating temporal dynamics in a generative model? Because as far as I know, is that you only learn the probability distribution of the generation, not the temporal dynamics itself. So how would you incorporate the temporal dynamics in a generative model? Sorry, it's a basic question.
In a generative model.
Yeah,
I would say in general, you can think of as a temporal model as something which outputs the next time step, but you can also think of a temporal model as outputting a chunk of time steps and iteratively refining this chunk of time steps. That's what the video models are doing. You basically have a chunk of latents, and you iteratively, via diffusion process, refine them. And also you can think of an LLM as outputting a whole text and then iteratively diffusing on this text. And this setup works for deterministic and probabilistic modeling. So you output in this landslide molecule paper, we output a whole trajectory, and over each time step in this trajectory is part of a flow matching process and gives you the probability.
Thank you so much.
Thank you.
Thank you. So Millard, do you want to unmute yourself and ask questions?
Sure. Am I audible?
Yes.
Okay, thanks for the great talk. So my question is about getting to the latent space. So I'm wondering, is there a way to identify how much we can do subsampling or like minimizing the number of supernodes before we get to the stage that we are having information loss, and then that affects the overall training of the model?
I would love to say obviously, but I think this is not an obvious question. The answer is unfortunately no. I think that in language, it's very intuitive for us how we tokenize, and basically you would look at a text and you just use a tokenize, and here we go. In engineering or in many of these challenges, this is absolutely not intuitive, and even getting the right way of how much information you can you really need to have in the latent space, how heavily you can subsample, how heavily you can compress. This is really something which is not very much explored. I very much advocate that there is a lot more research going in this direction, because this is actually really what is needed if you use latent space modeling. So I would love to say, yes, there is a concept. The sad answer is there needs to be research done in this area. But might also be exciting.
Thanks.
Awesome.
Maybe adding something. I work a lot with people who model this particle dynamics and something like it with discrete element methods. There's really there's works showing how small the number of degrees of freedom is actually is in a system of 100,000 particles, which is very motivating that this latent space maybe can really be very, very small.
Related, before going into Luning's questions, was the Millard ask about the self-sampling. If you go back to the UPT encoding of physical system slide, probably in the beginning, and I see that self-sampling is very structured. It doesn't look like a random. If you can elaborate more on this specific examples, how you chose those self-sampling strategy.
That's a good point. That's actually an error in the sketch. So obviously this should be a bit more random, not so structure preserving. But it's a very good point. So the way we currently subsampling many of these problems, you have an underlying mesh, and this underlying mesh is in simulations. A mesh is always very fine-grained when there is a lot of variation, when the gradient between different mesh cells is very large, and then when it flows or whatever physics gets laminar, the mesh cells get larger and larger. So if you just sample randomly according to each mesh cell, basically preserve more information where there is finer mesh cells and when more physics is happening. That's a very good sampling strategy. Obviously, I don't think it's the best sampling strategy. I generally, from an information perspective, and I have people looking into that, this subsampling is a very fundamental question to ask. I don't have the answer what to do it. I just have the feeling that this might be something which is worth doing really proper research.
Yeah, totally agree. Okay, thank you. Luning, do you want to unmute yourself and ask questions?
Okay, yeah. Hi, thank you, Yang-Su, for letting me ask the question, and thank you, Professor, for the great talk. I also love the idea of learning those dynamics in the latent space, and recently I'm working on some data set come from molecular dynamics or phase field modeling, and they basically involve some fundamental process like the spinodal decomposition and dendrite growth, and they are all very local dynamics. The material scientists, they are very interested in, for example, learning on a smaller graph and directly evaluate them on a larger graph. And they already show that it is possible even without any further training, like zero-shot extrapolation on the larger domain. But if I trying to do any, introduce any encoder-decoder process, I just feel the spatial extrapolation becomes very worse. So I'm not sure if you have come across similar problem and such kind of your latent space modeling. Could you, have some, I'm just curious. Have you ever faced those kind of problem, and do you have any idea to make it, make it better, or it is just not possible?
No, this is a very good question. I would say what latent diffusion is telling us, that basically you can have this lossless compression, and this latent space modeling works extremely well. However, in many of these cases, as you correctly pointed out, it's very hard to get that to work. So the name of the game is first how to get these very good encodings. I mean, in the end, also for this molecular dynamics paper, it was the most challenging part, or basically 90% of the work, or this big breakthrough of Florian, was to get a lossless encoding of molecules in a space which is unstructured. If you have that, then running the diffusion model or whatnot is basically just a plug and play. So I think what your question is more or less my scheme of the talk, that latent space modeling is extremely powerful. The research in our areas, like in science and engineering, should be really focused of how we get to such a good latent space representation. It's not so clear. It's not as clear as it is in language and as it is in vision. So my experience, to maybe answer the question at least a bit, is that we always got it to work, but it depended on the problem, and it was sometimes extremely hard, and it always needed some kind of tricks to make it to work.
Okay, well, thank you.
Probably not satisfying, but
all right. Okay, so let me ask another question. I was pretty fascinated by that ID-based tracking idea that your smarter students came up with.
yes.
Can you elaborate more? I'm puzzled. Okay, so you said the input token not only includes the features and positions of each individual molecules, but also you assign some sort of ID to it, and then you put it into the encoder. And I'm wondering what's the size of that input token, and that's it. That corresponds to individual molecules.
So
and yeah.
So each ID is basically so each atom gets assigned an ID. So if it's carbon atom, you would get I don't know ID 7. If it's a hydrogen atom, you would get ID 3 or whatever. And then basically this is so you have you run your ID through some sort of film encoding, and then you stack positions and features together, and that's your input vector. So what you have to do is you have to have a list of IDs, and those IDs obviously have to correspond to different atoms, because what you would then do in the decoding, you would basically give the list of IDs, and this list of IDs corresponds obviously to the number of atoms, and the decoder would give you back the positions. So in that way, the knowledge or the inductive bias you have is to tell the decoder what are the atoms you want to retrieve. You can give the decoder obviously a different number of lists, and it would give you something back, but obviously then it's physically not correct.
Okay, so the decoder does not output the ID.
It outputs the position based on the ID.
Based on
It's you can think of it. It's a reversed field. Normally you would output the position, you get in a value. Here you put in the ID and you get the position out.
Okay, interesting. I will definitely look in to the paper and get the more details out of it. Okay, Rausel, do you want to unmute and ask your questions directly?
Oh, hello. So yes, thank you for a wonderful talk. So my question is a bit more general. It's kind of like, where should we go from here? So do you believe we should kind of like impose like some structure in these latent spaces, or especially to improve out of distribution generalization, or do you believe we should just let them free and just let the encoders learn for themselves? So yeah, what do you think?
It's a good question. I hear myself. Can you maybe
Yeah,
mute
Russell, if you can mute. Okay, I can mute him.
I would say that starting with a latent space modeling, all this the game starts fresh. So the question of how good we can generalize, how good how consistent we can be, and so on and so forth. This needs all to be tested and re-evaluated, because many things are just very different the way you model it. I would definitely say that the time modeling can be done very differently, which allows us to do a lot of nice properties. Also, with these generative models, you have much more flexibility, which I think relates a bit to getting out of distribution better under control. But there is not, I also cannot give a satisfying answer, except that now when we basically know how we tokenize and model new problems, we have to kind of redo all these studies we did before.
Okay, great. Thank you.
Thank you very much.
Is there any other questions? I'm debating myself whether I'm going to ask this question or not. So that NL, the numerical. Hello, Isaac. Oh, so you have a question?
Yeah, can I ask a quick question?
Oh, yeah. Go ahead.
Yeah, thank you. Overall, like, it's a great talk. I've been following your work, and so I just like want to ask like a very general question. Like, so do you think there might be a latent space that kind of allows us to learn some, multi-skill features, because when you kind of give the motivations earlier, basically the modeling often the case are, have different skills, and do you think this latent representation being like encoder handling different skill, and that kind of we can have some uniform representation on this latents, that that would be like very efficient to represent like some physical systems. Yeah.
It's a great question. So the way I presented this of having these two different modalities, I call them physics modalities, like particles and fluids interacting with each other. You can also think of two different scales interacting with each other. So basically, if you have a multi-scale problem, you can use different encoders or different tokens for each scale, and in the latent space let these tokens interact with each other. I think the conceptual leap is to identify what you see as a different modality in your problem, and that can be anything. That can be material, that can be scale, that can be I don't know, and then let these different tokens do the magic in the latent space. This is how I would model multi-scale, and not saying that I'm doing it right now, but I have very, very similar ideas.
Yeah, sounds great. Yeah, thanks.
Awesome. Okay, well, is there any other questions? I think it's time's up. I'm sure, Johannes, you have another schedule for the conference.
Thank you very much for having me, and thanks for the amazing questions. That was very, very encouraging and very, very cool to see.
Johannes, I mean, you actually bombed us with so many exciting the models you have developed so far. So thank you so much for that.
Thank you so much for having me.
All right.
Greetings to the West Coast.
All right, let me stop the recording.